So today I want to actually start with some more down to earth motivation and access to some real mathematics again. Let me talk a bit about p-adic theory over very algebraically closed fields. So in fact, it's not important that I take really the completion of the algebraic closure of QP. I could take any C of a QP, which is an algebraically closed non-Archimedean field. Some other notation, it has a ring of integers. Yeah, non-Archimedean and somehow implies complete for me. Ring of integers. OC and residue fields. Okay. And so, I guess in p-adic theory, you look at the p-adic cohomologies associated with some algebraic varieties over these gadgets, or also associated with p-divisible groups, which form somehow a good model for the cohomology you would get from abelian varieties. So let G be a p-divisible group over a ring of integers, which has some Tate module. Symmetrical multiplication by p over the p to the n torsion of G. So that's some finite free ZP module. And so if you have by theorem of Tate, if you have a p-divisible group over a finite extension of QP, then if you tensor this ZP module with CP, say, then this decomposes as a Gauss module into a part which is just a vector space of a CP and one which is a Tate twist. There's a version of this over for p-divisible groups which are just defined over OC, not over something discretely valued. But in this case, it's just a filtration, so there's a Hodge-Tate short exact sequence. Like the following. We have the Tate module of G, tensor it up to C. And then there is a natural map, maybe called alpha of G, which goes to the dual of the Lie algebra of the dual abelian variety. So G dual was the dual abelian variety. Dual p-divisible group, sorry. Which is something which lives over OC, and so we just invert P. And then the kernel is something similar. This time it's a Lie algebra of C. And then you tensor it up to C, but you need to do a Tate twist by 1. And so this map is somehow a dual map, or more precisely, it's the dual of the map for the dual p-divisible group twisted by 1.
So what do you mean by C of 1 when
Yeah, it doesn't really matter much. But if my p-divisible group happened to be defined over a smaller field, in order to make this Galois covariant, I would have to include the Tate twist. I mean, so to make it a canonical map, I have to include the Tate twist. And I guess Fark someone gave a more detailed version of this result. And so actually, this map alpha G here is very easy to define. If you have an element in the Tate module, And so you can also think of the Tate module as being maps of p-divisible groups from QP mod ZP to G. Because any section of a C of this finite group scheme actually extends to OC. So the sections of a C are the same as over OC. And that's the same as a map from Z mod P to the NZ into your group G. And then assembling them, you get a map from QP mod ZP into G. So if you have such an element in here, then you can look at the dual map, which is a map from the dual p-divisible group to mu p infinity. Then you can look at the induced map on Lie algebras. It's a map from the Lie algebra of G dual to the Lie algebra of mu p infinity. But that's like canonically trivialized if you want, like standard differentials like dt over t. And so there is an element of the dual of the Lie algebra of the dual. So actually, this map here would be defined without inverting p, but the sequence would not be exact then. But you can bound the p torsion that appears in the cohomology. It's very small. It's killed by like a p minus 1's root of p. But we will only need this kind of rational state. So alpha G is very easy to define, and but it's not even clear, so not easy to see that. If you compose those two maps, that the composition is actually trivial. So I don't know any proof that doesn't simultaneously prove everything. Although some, like I told you all the definitions, so you can try to prove this, but I don't know how to do this really. Okay, so so this way we can get the following kind of nice functor. So it goes from p-divisible groups over OC to the following data, TW, where T is the finite free ZP module. And W in T tensor up to C is a subvector space, sub-C vector space. Which is the obvious signal. So you send G to its Tate module. And the subvector space which you have there, so that is the Lie algebra tensor over CC of 1. And then in my joint work with Jared Weinstein, we proved that this is actually an equivalence of categories. Alright, so we can somewhat classify, so that's roughly similar to the classification of Hebrew varieties over the complex numbers, which are also classified by the first singular homology and the Hodge filtration which you have on it. Except that here it's a slightly low.
What about the dimension of W?
The dimension of W here can be arbitrary because you have like the dimension and the height of a p-divisible group can be like arbitrary, subject to the constraints. So that T, the dimension of T is like the height of the p-divisible group, and the dimension of W is the dimension. Yeah, the dimension of this p-divisible group. That can be arbitrary. Great. And so so now we get the following diagram. So we have here p-divisible groups over OC. So they are classified by such pairs TW as above. On the other hand, there is an obvious functor from p-divisible groups over the ring of integers to p-divisible groups over the residue field. Just reduction. But this we know by Dieudonné theory. It's classified by the following kind of linear algebra data. So by M, a finite free module over the ring of bit vectors, plus a Frobenius linear map, and Frobenius inverse linear map, satisfying that they commute and their composition is P. And so this functor was pretty obvious, so we would think that there is some kind of obvious functor here. But it's probably not so clear. So the aim of the next few lectures is explain this functor. And so, of course, this functor is some kind of comparison functor between its hard cohomology, which we're looking at here, and crystalline cohomology, which we're looking at down here. And so, if G happened to be defined over the ring of integers k of k, where k over qp, say, is finite, then you could recover the M as the p-adic Tate module of G tensored to the subperiod ring A Chris, probably defined, and then take GK invariance at least up to p torsion. So that's like von 10 star. But even in this case, it's not so easy to actually say gives a correct integral thing here, like especially if p is 2. But I mean, this totally breaks down in our situation where we're working with C because there's no Gauss group action here. So. Okay. All right. So today I'll try to explain how this functor is defined, and then we will have to do some extra work to get all the steps in the next lectures. And so the first step, actually, to do this is to give a linear algebra description in terms of very much such data T and W as there. Oh, Stuke. Magnetic spectrum, C flat. With one paw. Let's see. In the sense of the last lecture. So, except that now now C is this characteristic zero field when it was a characteristic P field last time. So let me introduce some notation and remind you of other notation for these objects. OC flat ring of integers. So OC flat is classically also called R by Fontaine, or it's also called E tilde plus by Berger and Colmes. And then this gadget here, I'm not sure whether it has a name besides frac R in this in Fontaine's world, but it would be called E tilde without the plus by Berger and Colmes. Okay, so then last time I was considering this ring A inf, which is a ring of bit vectors of this ring of integers here. So that's what's also called W of R. So that's all Fontaine style notation, and then it's called A tilde plus in the Berger-Colmes world. And so this admits a map theta, a surjective map to the ring of integers of C, and the kernel of theta is generated by a non-zero divisor psi, which we can take to be p minus something I will call p flat. And again, there are probably different notations for this guy, where p flat is this element corresponding to this sequence of p power roots of p in the tilde. And so under theta, both of these guys are mapped to p, and so the difference is 0. All right. And so, yeah. So we have the p-adic spectrum now of this guy. And so I will draw a picture here. And so points will always be labeled by residue fields. Where I will already give a name to the ring of bit vectors of k invert p. So that's, at least by people like Kottwitz, it's called L. So, all right, so there's a special point whose residue field is k. Then there was, like, we have 2 points in the locus where p is equal to 0. The other one has residue field C flat. And then there was 1 point here whose residue field is then L, where this forms the locus where the Teichmüller of p flat is 0. And then there's another point corresponding to this map theta. So you have somewhere here a point one should then call xc. There's some of this diagonal locus here is the locus where p is equal to pi flat. Okay, and so as before, there's this map kappa, which maps the complement of the closed point to 0, infinity. Whereas this point here, this is mapped to 1. And so in general, this kappa is measuring like the variation of p in terms of the variation of p flat. And so here they have the same, so you get 1. And so there is also a Frobenius map phi on this guy, because you have like phi acting by functoriality of the Witt vector constructor on A inf. And so phi on here is equal to multiplication by 1 over p. Okay. And so in this picture, the space where Stukas lived was a locus where p flat is not 0. And so let's call this open subset here U. Or no. That's what we call y0 infinity. Because it's precisely the preimage under kappa of this interval from 0 excluded to infinity. Okay. All right. Okay, some other rings. So there's one ring which always has the same notation, I think. It's called p-adic plus. So the simplest definition is that it is a p-adic completion of the surjection from A inf invert p to C. So that's a complete discrete valuation ring with residue field C and uniformizer psi. And so in terms of so in keeping this notation I used in an example earlier, let me call maybe X the adic spectrum and Y the adic spectrum removes a closed point. And anyway, so if you want, you can say it's the completed local ring of Y, or also X at this point X. And so I mean, this picture is really very similar to the picture of ZP power series T, so of a two-dimensional complete regular local ring. And so there it is the case that if you look at such a point of ranked 1 somehow, well, of height 1, and take the complete local ring there, then it's complete discrete valuation ring. Because it's like a codimension 1 thing inside something two-dimensional. All right. And
Is the description of measures over the punctured local ring that you can always extend?
yeah, so that's something I will talk about later. So something we will use later is that if I have a vector bundle on like this, what I call Y there, then actually it extends uniquely to a vector bundle on all of X. So that's a property that's somehow unique to two-dimensional regular local rings. And so other notation that's unambiguous is what's p-adic, so that's fraction field of p-adic plus. Or I mean, you really just have to invert this element psi. Good. And so another theorem, which is probably implicit in the work of Fark, is that you have the following linear algebra description of what Stukas are. Stukas over there are just pairs T and some lattice that for some reason I started calling psi. Did you start this? I don't know. Finite free ZP module. And psi inside of T tensor beta ram is a beta ram plus lattice. So this is really like in discretely valued fields, there's a very good notion of lattice. It's a finitely generated submodule, which after inverting the uniformizer gives this vector space. So what does this have to do with our pairs TW? So, note, where's the functor? Which of course is the identity on Xi, and so on T, and Xi is defined to be those elements X in T tensor ZP beta round plus, such that modulo the uniformizer they lie in the subspace W. So it's like an elementary modification of the standard beta round plus lattice which you have inside there. So this way we can start from this kind of linear algebra data and build a Stuka. And then the other steps I want to explain is that one can then actually extend this Stuka to all of A-inf, and then one can reduce to this part here of WK and get the Dieudonné module. That will be the outline.
Peter?
Yeah?
So for this statement here about the completed local ring,
Yeah?
so in what I mean, given that these A-inf rings are kind of huge, so in what generality is it the case that when you want to compute the completed local ring on some p-adic space, that you can, calculate it as like a commutative algebra completion, like an algebraic localization? I mean, is there some general statement, or you just, this one maybe you just do directly, but is there some general?
So in this one I was convinced that you can do it directly, but I didn't figure out.
Checking this in this case, this was not completely evident.
No.
Not difficult.
Yeah.
It's not like some general.
I don't have a general
okay.
statement in my head. Well, I guess what you try to prove is that even after you pass like rational neighborhoods of this point, this psi will still generate the kernel, and so it's still complete discrete variation ring, the same residual field, same uniformizer.
This is a fully faithful functor?
Which functor? This functor here from T dot? Yes. Yes. So that's precisely parameterizing like those lattices psi which are in like with relative position to the standard lattice is like bounded between like constant 0 and constant 1.
That only stick a little bit. I mean, so in other words, this is the essential image. In other words, corresponding to those lattices which are between psi inverse of,
Yeah. So those which are between this lattice and like psi times this lattice.
Right.
Yeah. And so today I want to prove this theorem. So take some preparation. So let's consider another ring. That's called the integral robber ring, I think. So that's Kidd-Lyar notation. And so in terms of this curve, you can define it as, or in terms of this y, you can define it just as a local ring at this point x C flat. So actually, how can one describe this? So if I have t less than infinity, a rational number, I let y from t to infinity be the inverse image of this interval. But actually I have to take the interior.
Don't you take the plus or y?
No.
Okay.
No. If I would take the plus,
Is this
I mean, p is not invertible even in here, right? Because let's like close to the point where p is equal to 0, so p doesn't get invertible there.
Okay. That's good.
Yeah.
is this a tilde dagger?
It's probably a tilde.
No, this is the ring of
Yes,
integral.
yes, yes.
The ring of integral.
No. It's a tilde dagger. A tilde dagger. That's cool.
Yeah.
I mean, the notation is confusing, but I don't know. Like for people who different sets of notation, I thought it's better if I include all of them. And like for people who don't know any notation, I try to give a definition. So more precisely, that's the locus of all points x, such that the absolute value of p at x is at most the absolute value of p flat to the t. And this being non-zero inside of the adic spectrum thing. In fact, contained in y.
What does interior refer to?
Well, there are some strange rank 2 points that are sticking out here, where the evaluation of this is infinitesimally bigger than that, and I don't want them. They would, so this is a rational subset if I put like the strict inequality here, but if I would take this strict pre-image, I would have some one extra rank 2 point, which would prevent this from being a rational subset. So that's like purely technical. So that's a rational subset. And so you can evaluate the structure sheaf on this guy. And again, that is a ring which has tons of different names. So first of all, what is it? It's the sum, those series Rn times p to the n greater or equal to 0. Where the Rn are in the tilde, not necessarily integral. And you have some convergence condition for them, which in my notation I think means that this expression goes to 0. So if I would like put p over p flat to the t there, then this would just be the condition would be just as the coefficients go to 0. So in the notation of my last lecture, this would be R adjoint p over p flat to the t. And what other notation are there? So Kidd-Lyar would call this R the integral robber ring of radius r, where r is 1 over t. So in my case is t goes to infinity, and so in Kedlaya's case is r would go to 0. And so in Colmes's notation, that's a tilde 0 r. Where fortunately it's actually the same r, I think. So let me keep this picture up. Good. So so what properties does this ring have? So it's a it's a Henselian local ring. Whose residue field C flat. And actually, its completion is just the ring of fit vectors of C flat. And so on this host on AINF, you had this Frobenius automorphism phi, and so phi is also an automorphism of this guy, but like if you are doing this at a finite level, so like for one of these rings R. So of course I should say that an R tilde int is just the direct limit of these rings because it's not a local ring.
Discrete variation, the R tilde int.
It's a discrete variation ring, yeah.
Maybe not.
It's a Henselian discrete variation ring. That's probably better than local. And it's a complete discrete variation rings. Then the ring of fit vectors. Because phi somehow contracts everything away from this point p equal to 0, if you have a function on some radius, well, phi won't preserve these subrings, but instead it will only give a function defined on a smaller thing. And so in the direct limit over R, you get that phi is an automorphism of.
Yeah. It's one of it.
No, I think that's correct. So, I mean, if it was PR, then there would be a restriction map to R int R.
But here we got you for 5, which
Well,
might be 1 over.
R is 1 over T, yeah?
Yes.
So T is very big. So, I mean, it's if I put T here, if I would parameterize in terms of T, then I would have to put PT here. But if I do it in terms of R, I think. So I know for a fact that phi does not act on, like, there's no map with the same R. And to make this correct, I think it has to be R over P.
You're preserving the geometric side, which you don't want.
Yeah, but on the geometric side it goes the other way around. So you want it to.
If you replace this T by PT, then you're shrinking the geometric, which means you're preserving the right. You don't want that.
What?
I mean,
Do you disagree with what's written, or?
On on the geometry, should phi is not contracting that line. It's dilating at p equals 0 pi.
Yeah, but some of the phi on functions is somehow the pullback under phi on the geometric space, right? And so, like, if I think it's correct as written. If not, it's the direction of phi that I've drawn there.
Yeah, that's right. Phi decreases t by p. It increases r. So geometrically, it increases r. So on the level of rings, it should decrease r, which is what you're doing.
Yeah, thank you.
We are ganged up together.
I was very confused when preparing the lecture, right? I hope I figured this out correctly. So in the following, I want to talk about lots of phi modules, and I want to give a definition in general where I can't specify the base ring really. So whenever I say phi module over some ring which I don't specify, which probably has an automorphism called phi, so that's supposed to be a finite projective module.
Why is there a quotation mark?
Well, like it's some kind of meta definition because you can also erase them. It's a finite projective module. This is phi semilinear isomorphism phi m. So this applies whenever I have a base ring A with an Froben's automorphism phi. But I also want this in the context where this will probably be a sheaf of rings on some space. And so, like.
Do you mean the isomorphism? You mean from the linearized version?
Well, I mean, phi will be always an automorphism on the base ring.
Oh, really?
Yeah. Because I'm working in this, with these perfect rings, where this is okay. And so let's first of all try to we want to understand some kind of phi modules, not in this sense because I will have a singular point over this set U. But first of all, we try to understand them very close to this point p equal to 0. And so there's a theorem of Kedlaya, which is probably actually he has versions of this which are much stronger than what I'm writing. That phi modules over this local ring, the integral rubber ring, go by a base extension isomorphically to phi modules over the ring of bit vectors of C flat. And this is just isomorphic to the category of finite free ZP modules. Meaning that while close to this point p equal to 0, the datum of this phi module is really just the datum of a finite free ZP module. So what are the functors here? So that's just base extension, of course.
That's easier than what Kedlaya is.
Yeah, I said that. I mean, that's much easier than.
And that
but
was proved much before.
It was okay. So who proved it then?
I don't know. Maybe me and Charbonnier or. But that's easy.
Sorry. 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 Okay. Also you have a much deeper theorem, which is over the non-perfect guy where you can descend. But this is so this is easy. So I will explain how this is done. And so that's the functor of phi invariance. Okay, so let's call this 1 and 2. So, remarks about this? To the special case of the following result, that if you R is any perfect ring, then phi modules over the ring of bit vectors are equivalent to ZP local systems on spec R. And so in particular, if R happens to be an algebraically closed field, as is the case here, then all of those are trivial and they are just given by the fiber at this geometric point, which is a finite free ZP module. And like such a theorem is sometimes called, I don't know, Artin-Schreier-Witt theory or so. And like the hard part is probably if you like, there is a version over just the ring R itself, phi modules over R, and there's those FP local systems, and like you have to show that whenever you have a phi module over R, then finite eta locally it has enough phi invariance, but you can just write down the universal scheme which parameterizes phi invariance, and you see directly from the Jacobian criterion that this is finite eta. And so if you look at the functor of 1, then any such guy here is free by this result too, so it's clearly essentially surjective. So remains as fully faithful. And so that's equivalent to the statement that if I have M over this ring, integral rubber ring, a phi module, then all the phi invariant sections I get after extending scalars to the bit vectors already come from M. And this can be done by a consideration of Newton polygons. So it's a statement about the growth of the coefficients of these phi invariant sections. But if you know that the matrix is defining this matrix phi or something, have some growth condition, you can use the same for.
I'm just confused. It doesn't follow from 2?
Doesn't it follow from 2? I don't think so. I think you really have to prove this statement separately. Why should it follow from 2?
If you have some invariance, have some invariant thing over the. Anyway, okay.
No, I think you really have to do some kind of argument which will involve some estimates then. Okay. Okay, so now we understand the situation very close to this point there. And now we want to extend to a larger part of the space. And so actually, you can extend any phi module over like this integral rubber ring canonically to all of this curve here. from 0 to infinity, which one might also call Stukas with no poles, with no pause. That goes isomorphically to phi modules over ring, which then, by the previous result, are just finite free ZP modules. And again, this is a simple observation, which I don't know whom to attribute it to, so I take suggestions. But, so how is this proved? So if I have n, a phi module over this R tilde int, then giving such a phi module is just a finite, well, this locus of free module, so that's defined on some of these guys here, and then the matrix giving this phi linear automorphism is also has entries in one of these rings, so actually everything that is defined in an actual neighborhood. So there exists some MR over some integral guy. And phi and automorphism, phi MR, between MR and M, what one called MR over P, which is defined to be just length tangent to that bigger ring, giving rise to it. And also this MR is essentially uniquely determined, meaning that any two choices will become equal after making R smaller. And so okay, so this follows from finite presentation plus the fact that this ring is the direct limit of these. But then everything is somehow, you have a Frobenius automorphism which maps the situation over some radius S isomorphic to the situation over S over P. And so you can just pull back the situation under Frobenius a couple of times. Pull back. And this way you get a unique extension to the union over all phi to the n. Which is okay. So some of the whole procedure we're trying to do is that we're somebody so what this tells us is that Tarkomon determines something in a neighborhood. Then this lattice will be something that comes in here. So there we have to modify this module where phi is an automorphism. So then we get something all over here. And eventually crystalline cohomodule will be something that lives here. And so then we will have to extend this whole picture over this. All right. So the next step I want to do is modify this guy at this point here to take account of this lattice psi. So E phi E. Okay, and so then something we can do is if we have such a Stuka, we can restrict to a small neighborhood here, where phi then will become an automorphism because only here something non-trivial happens. And so this way you get a phi module over this integral rubber ring. So restrict to and then we can extend to a new phi module over this whole guy again. And so what we're getting is we're getting a Stuka, let's call it E0, phi E0, with no pause. Which in fact, by this equivalence of categories, what is it really? So we have E0 is just T tensor ZP with a structure sheaf, where T is what you get by taking the Stuka, taking the complete local guy. So that's now phi module over WC flat. Taking phi invariant there and then extending over again. So this E0 is just determined in terms of this finite free ZP module T. And so, so the two are isomorphic over the integral rubber ring, but it's actually in a small neighborhood, and then we can spread this neighborhood so long as phi is also an automorphism on E. So E is isomorphic.
Sorry, can you just clarify what you mean when you say you start with this thing with one bar?
Yeah.
What are you restricting to artificially?
This E is phi E. So I'm taking this local ring of E at this point, if you like. So that's a phi module over the integral rubber ring.
Oh, okay.
Orange after all was the local ring at that point at C flat.
Yeah.
C flat.
Extend to it, yeah.
And this extension process involves using Frobenius? What is it?
I mean, that's this for extension procedure there.
Oh,
Yeah.
and that is you just apply this
Yes.
proposition.
Yes. Yes. And so by construction, our E is isomorphic to E0 over the integral rubber ring. And so this implies that the same is true for some very small r. But then prime as long as not reaching the pole. And so what this analysis gives you is that for t greater than 1 over p, the restriction of E to this curve yt infinity, which actually does include this point. And the phi, which is an automorphism between E restricted to this part from t to infinity with E restricted to the part from pt to infinity. is isomorphic to the same thing with E0. Okay? And so as for the integral robbering, to get this isomorphism semi-linear guy, you have to put these intervals. And so on this part it's still an isomorphism because here this point xc is not included. But now if t is less than 1, then this point xc is now in here. So there's some action happening here which we can then reflect on the other side. So more precisely, if I apply this automorphism phi of E to the complete local ring of E at the image of phi, so somewhere here we have phi of xc. So this is a lattice, this is contained in E at xc completed. Tensor Biedermann plus Biedermann. So away from this point, so if I work psi, this phi is still an automorphism. So rationally they are the same, but this gives like a different lattice in there. So Biedermann plus lattice. And so this is now identified with E0 completed at xc tensor. And I recall that E0 was just like this constant extension from like this constant vector bundle associated with this finite free ZP module. So that extension here is really just T tensor ZP Biedermann. So the data of what happens at this paw determines this Biedermann plus lattice there. T tensor Biedermann.
About this point, or is it just for compatibility with p-adic theory?
Well, no, I mean, like in Tuesday's lecture, I was starting with a field of characteristic P and then picking a point on the curve, which gave me an untilted characteristic 0. And today I was starting off the other way. I was picking the field in characteristic 0, which gives me the tilt with a point. But really, if you're starting from the perspective of this field C flat, there's really nothing special about this point xc there.
But even from the perspective of characteristic 0, you don't have because this is C.
Yeah. Yes. And really, everything I'm saying today could be extended to the case of Stukas with several paws. It's just more notation. You have to like, keep like check of filtration at each point and blah blah blah.
Is this the only point where you see C?
No, I mean, there can be many other points because you feel CP, but it's like, if you start with something that has a canonical point, which someone exactly, by what I said before, someone exactly memorizes, that you started with something in characteristic 0. In fact, it could be that all points, like all untilts, are isomorphic to CP. It's not known whether this is actually true. So if you start with something spherically complete, then I think it's true that all the residue fields are the same. They're all the same field C. Where am I? So here. Okay, so This way we actually get the functor. I promised to prove is an equivalent. This defines the functor from is 1 pair at C, 2 pairs. And I mean, when I said, I meant all my Stukas to now have meromorphic pairs. So otherwise, inverting C algebraically wouldn't be enough, but I would have to do some kind of the wrong series. Okay. And so, so this defines this functor, but actually there's also a functor in the other way. So it can also. So we get the E0, phi E0, which is just this. This thing. And so then we want to modify to get the desired vector bundle. And so we also have this lattice psi, which we now can consider as being a lattice inside of the complete local ring of this vector bundle, tensors of speed around. And so actually we have to modify our vector bundle not just at one point, but at all the other iterates as well, because we want Frobenius to be an isomorphism after that as well. So we have to change it accordingly there. So, but actually, if you have a lattice there, then also at all the phi iterates we get lattices. So phi E0, and now I might be off by signs here, but I think it's right. So I want also lattices at all the iterates of this point, x, c. For all n greater or equal to 1. Where so this is a module over the complete local ring of y at this ith iterate, but via in this direction, I think. No, in this direction. Phi to the n. That should be isomorphic to the complete local ring of y, which is beta 1 plus. So phi identifies the complete local rings at those 2 points, so we can still consider this as a beta 1 plus module. All right. And so somewhere we have here is a 0.5 xc phi squared of xc, and then all the other iterates. And so we can modify because we are in this discretely valued situation, we can modify E0 at all the phi to the n xc n greater or equal to 1 using this lattice. And so, although there's infinitely many modifications really on any affinoid subset of it, there's only finitely many modifications happening, so that's fine. And so this way we get a new vector bundle. E over this whole thing. together with now an automorphism phi e between the pullback restricted to y 0 infinity. But exactly at this point xc it will now have a pole. So it's clear that it's an automorphism at all points different from some iterates of xc under the Frobenius. But then the first step where we do a modification, something happens there. But after that, we have somehow done the same compatible modification at the 2 points. And so it's really an automorphism there. All right. And so I think these arguments should finish step 1. Which I recall was that Stuka's always sparsely flat. There's one pole, there's one meromorphic pole. Let's see, are equivalent to pairs T. So. And so, what I will then explain in the next lectures, step 2 and 3, so they are the following. Step 2 is that any Stuka over extends to all of y, meaning there's just one point extra, so this point xl. And once you've done that extension, step 3 is to extend also to the last remaining point. So any, it still causes Stuka over y extends to all of x. L was the fraction field of W of k, yes.
So do we really want to think about this spot in the non-adic space to multi-logically relevant? Just concretely, you're just going to build some...
Yes, yes.
It's the projected A-inch module.
No, actually, so I can at least prove that this y is an honest adic space, and then after that it's somewhat, it doesn't really matter.
We do kind of want that y is an honest adic space for the argument.
Yeah. Well, I will explain it next time. So. So given these steps, we finally get this theorem of Fark about the classification of Brachisi modules. So in the end, what you get after extending all this y is what I called the Brachisi module last time. Over this ring A inf. That's also just equivalent to pairs T xi.
And this proof is very different from the one we found?
I think this proof is different, or is it not?
Up to now, it's not different. I mean, I have not seen step 2 and step 3.
Okay.
But it doesn't seem to be more conceptual.
Now, I mean, this last step is really just a statement that any vector bundle like this punctured spectrum can be extended to the whole thing, which I find quite conceptual. But in steps 2, I will use that phi modulus over b extend to phi modulus over b plus. Yes, yes, yes. Yes, that's in 2.
And something I need is matrix factorization.
Yeah, yeah, that's probably more or less equivalent to this extending vector bundles thing.
I have to finish
Yeah. Okay, and so now there's an obvious functor to D-U-N modules, so an obvious functor from to D-U-N modules, more precisely to the following kind of thing, to plus the sigma linear automorphism of the rational guy, which need not preserve the lattice. Like, if I have Bragg-Keesing modules, phi is not required to preserve the module. It could have some poles. So which just sends a module. This guy. And so I can come back to the question from the beginning of the lecture. So now we have the following diagram. So we have p-divisible groups over OC. They're equivalent to such pairs TW. They embed into the category of such T size. And this, by the theorem, can be enhanced to Bragg-Keesing modules. Which can then be reduced to D-U-N modules in this sense there. And so there is this other obvious functor as a reduction map. And those embed fully faithfully into D-U-N modules. And so the proposition is that this diagram commutes, and I would like to attribute this to somebody. Can you prove this?
Yes, of course.
I have to be
Okay.
I mean,
If P is different from 2, okay?
I think you can also do this with PS2. So, so this works integrally even for p equal to 2.
I'm not sure. This is you for P question. Not responsible.
Okay. Responsibility Scholze.
In the D-U-N modules, they can be made into a Tanaka category by sort of not existing in sigma anymore. Is there something similar here?
Sorry?
Can you, by the D-U-N modules, we don't insist that the thing is sigma linear, but have sigma n linear, some n.
Well, you can also already tensor them with sigma linear, right? What do you mean? When, so this forms the Tanaka category, these D-U-N modules, as do Bragg-Keesing modules. Okay, so that's it for today.